Hi, I'm Matt, and I work on the AMD GPU backend, and I'm going to talk about the semantics of address spaces in LLVM IR. So most people seem to go through their compiler lives without really caring about address spaces, so as an introduction, an address space at its most abstract description, it's a way of expressing properties of pointers. We have a few fields in the data layout to control these, but there are not that many properties you can really control. It's really part of the pointer type itself. It's not necessarily a property of the memory it points at. And it does not necessarily correspond to the hardware or language concepts of address spaces. It may, and it's commonly that you can map between these, but it does not necessarily have to be the case. The hand-wavy thing the langref says is they have target-defined semantics, but there are limits on what that really means, which is what I'm going to talk about. So your front-end relationship, as I said, it does not necessarily have anything to do with the IR address space. If you have a language like OpenCL, you have explicit address spaces in the source code. And for a GPU target, like AMD GPU, Clang pretty much directly maps those into some IR address space equivalent. But for x86, for example, it discards all these as a mapping function, and you can configure that in Clang. But that's a front-end thing. The front-end needs to be aware of how to map the address spaces of the language to the target. It is possible to use front-end, for front-end to use pointers with address spaces for some other purpose that the language or runtime knows. However, this, to some extent, is an undocumented property that I think works by accident. If you look at how selection.dag is implemented, there is all pointer types don't exist, everything's lowered to an integer, and the default load and store patterns ignore the address space. So it happens to work out that for most targets, if you just code gen address spaces, it works out as you would expect. However, I didn't find anywhere this was explicitly documented. And this does not necessarily work for free in global ISO, where there are explicit pointer types per address space. So you would have to actually consciously implement this. So we should have targets start documenting range as usable for front-end specific purposes. There are a lot of possible uses. On GPUs, we have all these memory segments that are not necessarily in main memory. So weird embedded memories off chip are possible uses. You could do tag pointers or garbage collection references. We do have in the GPU one address space that's essentially used because we have 64-bit pointers, but in this case, we know the high bits at compile time. So by treating that as an address space cast from a 32-bit address space, we can save 32-bit single register for the ABI. We do also use address spaces to indicate that memory is constant. However, at least in the AIM GPU case, I'm not entirely happy with this because we do have other ways of representing this in the IR, although it's incomplete. I mean, like we have the invariant load metadata, which you could use instead for the most part. So there are a handful of properties that address spaces can control for you. The first basic one is just the pointer size alignment. And that means, yes, multiple pointer sizes in one program do work. This has worked for quite some time. There are some lingering passes that do assume a single pointer size, but those are mostly fixed. So the meaning of the bit value 0 pointer is the other major important one to worry about. 0 meaning an invalid pointer is only supposed to be assumed in address space 0. What happens when you dereference the pointer is sort of a property of the address space, and the pointer representation type, which I'll talk about in a little bit. So what most people are familiar with in LLVM IR is what's called the default address space, and an important point I would like to emphasize is that it is not the absence of an address space. There are I see a lot of posts on the mailing list and the occasional comment in the code with phrasing such as like if a value has an address space or in the presence of address spaces, but strictly speaking, this is not a correct way of thinking about or describing the situation because address space 0 is a distinct address space in its own right with its own properties. So address space 0 is a default in the sense that in the text form of the IR, it is not printed. It is not a generic address space in the sense that the CPU sees a flat memory and you can access any address through it. So it is not necessarily valid to cast any arbitrary address space to address space 0 or back. This is a target-specific property, and we don't have a defined way in the IR of telling anything that this is okay. There's only one pass where the concept of a flat addressing mode exists that uses target transform info. And the default address space has a small set of assumptions that optimizations use. So the set of assumptions it makes are not that big. The top one is that it behaves as an integer. Selection tag just lowers this to regular integer additions and multiplies and shifts and so forth. The size of an address space that isn't specified in the data layout explicitly assumes the default address space's size. And the null pointer has a bit value of 0, and it is undefined behavior to access it. However, this can be overridden with an attribute on functions. However, this isn't ideal because this isn't evaluated in constant expression context, for example. In any other address space, these assumptions are not supposed to be used. The bit value 0 pointer is a valid, potentially dereferenceable pointer. However, if you access a pointer that is not dereferenceable, it is still undefined behavior, I will argue, although it does not say this anywhere in the langref. A frequently asked question is about what address spaces mean for alias information, and the rule is by default, any address space may alias any other, including 0. And there's really no rules written for what it means to allocate anything in any address space. So one problematic area for AIM GPU is this handling of null pointers. So AIM GPU has 64 pointers that mostly behave like a normal CPU pointer as you would expect. Null is 0 and so forth. However, there are 3 address spaces where the pointer is really just a 32-bit offset. And that means 0 is actually a valid address, and it is where allocation begins. So there's currently really no first-class support for non-standard null pointers. There's just this vague description in the langref that you should assume 0 is a valid pointer for non-zero address spaces. So one point of confusion is there is this constant pointer null in the IR, which is printed as the word null. But that does not mean an invalid pointer. It means the bit value is 0 pointer, which is a kind of a problem. I think as a bike shedding problem, I would like to consider renaming all of these to something else like the invalid pointer value or sentinel pointer or something along those lines. But because we have all these other address spaces that do behave as you would expect with a null 0, we do not get the benefits of optimizations on these, and there's no way to opt into it. Another problem is front ends are responsible for inserting some alternative and know what the target wants. For example, you could have an int pointer from some invalid constant value. What we do for AIM GPU is we insert a constant expression cast from a default address space null, which will lower eventually to a -1. So we would like to benefit from optimizations in these non-zero address spaces with the null pointers, but also we'd like to optimize the invalid cases, although that's a bit less important because the languages that actually are used do not define null in the way that you might expect because there's just the one null value in C, for example, and that ends up meaning a generic null. There are definitely bugs with this non-zero null handling, but for some reason I don't see these come up in real code. I've never seen a bug report from any of these kind of issues, but there are theoretical problems I worry about. So this is something I would like to look into fixing in the future and add some kind of way of representing what the null pointer values are per address space of the data layout, which may involve renaming everything from null to avoid confusion with it meaning 0. So for an example of a bug that occurs today with non-zero null pointers is we have this non-null attribute and metadata in the IR. And there's sort of an inconsistent usage of null terminology or just confusion. If you interpret null as meaning the invalid pointer value, we miscompiled this today. So here's the most trivial example I could come up with that sort of shows this. So here you just have a pointer comparison with a non-null argument attribute and a comparison to a literal 0 and a literal -1. The important thing to note here is because of how C defines this, the 0 literal pointer ends up meaning a generic address space null. This is also a bit odd in this particular case because this is an OpenCL 1.2 example which did not define the concept of a generic address space. That was an OpenCL 2.0 feature, but we can code gen this okay and it's sort of not a problem, although it is a bit odd that there's this generic null pointer when there is no specific address space nulls in the language. But if you compile this, you get something, and simplify it a bit, you get something that looks like this. The second two here are more or less what you get out of Clang, where you have the constant expression cast from a generic null to the local address space. And the second case is an alternative we could use with an int pointer. The first case is the contrived example where I've manually used a zero value pointer. So if you run this through inscombine today, you get this, where the first case invalidly folds because it assumed that the bit val 0 meant an invalid pointer, which it is not, and that is invalid. The second case that we actually generate correctly folds, but this is, I think, an accident and not actually respecting what happened here. And the last case, we don't try to optimize at all, and it doesn't fold or do anything. So a frequently asked question on the mailing list is about address space alias analysis, and it is possible to handle this today. There is this thing called the external AA wrapper pass, where you can put whatever you want into it, including address space checks. It's a bit boilerplate heavy. It requires a full pass, and there's a lot of extra code to write. One minor issue here is if you look at how the address space and alias, or the aliasing pipeline is set up, it runs this last. However, in the AGPU case, the address space checks are trivial. So if we did this before anything else, including like basic AA, that would be a lot faster probably. Right now, it runs all these fancy alias analysis passes before it gets to this trivial check at the end. So it's impossible to talk about address spaces without talking about casting between them. So ADDRSPACECAST is an instruction that was added maybe 6 years ago or so for how to convert between address spaces. So the important thing is it might not be a no-op. It might change the pointer size or some other strange arbitrary representation change. It does give you strong aliasing properties, for example. This is, which you would not get if you did something like cast from a pointer to an integer and then integer to pointer, or did something where you casted a pointer to an integer and then did something with the high bits and then casted back to a pointer, because that would count as a capture in the IR model. So this is currently the only way to allow cast conversions between address spaces. Even if the pointer sizes match, bitcast is currently not allowed, although I would like to fix this at some point, because for the most part, targets have no-op address space casts, but you sort of can't opt out of the pessimizing assumptions of ADDRSPACECAST because it could make other changes. So it would be useful for no-op targets to not have to use ADDRSPACECAST in these trivial cases. So for an example of what a non-op ADDRSPACECAST looks like, this is the most interesting ADDRSPACECAST ANGPU implements. So in the first case, we have what's corresponds to an OpenCL local pointer casted to the generic address space, and the second example is the inverse. So it's not that complicated. So it starts out as a 32-bit pointer, and needs to go to 64-bit pointer. So what we have here is a load of the high bits from somewhere. Specifically where varies per subtarget, but it just gets the high 32 bits from somewhere. And then we need to convert non-standard null values. We need to convert from the -1 null value to the 0 null value, and then insert the high bits into the 64-bit value. And on the inverse case, we just need to do a null check and then extract the low bits. One minor defect that we have in CodeGen today is we don't have any way of getting to the non-null metadata. So even if we have no way of knowing in CodeGen that this is always non-null, so we could eliminate the compare and select. And this would just be a truncate and the merge values. So for GPUs, flat addresses exist on modern GPUs, but it can be slower. We have problems such as worse addressing modes in a flat address space, and we may need to wait for more types of memory. And the other problem we have is we may need to break it down, flat accesses, into 4-element pieces if it could potentially alias the stack. However, this concept of flat addressing only exists in the one pass in LLVM today, the infer address spaces pass. It generally does a pretty good job eliminating our casts, but it's not perfect, obviously. I still would like, once we do this, we mostly get the optimizations we would like because the address spaces go away and the casts go away, and most other passes work correctly. However, it still would be nice if generic passes understood ADDRSPACECAST to some degree. In particular, SROA, I would like to be aware of ADDRSPACECAST. There's been a patch that's been posted 4 or 5 times, and I'm not sure if it was ever committed or not, but So the way anything that looks like C++ works is you have your variable that is declared if it's a pointer and it becomes a stack object, and you have a point that is immediately casted to the generic address space. So then you have a pointer capture of that. So then there's the circular dependency because infer address spaces can't deal with values in memory. SROA gets them out of memory, but it also won't deal with the cast. So you have to run each of these multiple times to get rid of all your allocas that are casted, which is all of them. So I would like to define sufficient rules in the IR for SROA to eliminate these cases. So I have a proposal up on the Langref to define this. So the properties that SROA needs for this is the cast should be known reversible if the result is dereferenceable or null, or at least for integral address spaces. So SROA needs to does change the indexing and then casts back, but if the way ADDRSPACECAST is loosely defined is you could potentially have an operation that isn't reversible. But I think if you can actually do something with the result pointer, then you should be able to go back in some way. Another minor point is SROA can change the address space of the access because it can discover that so SROA doesn't always fully eliminate locas. It will sometimes change them and break them down into different types. But then it will try to produce operations in the original address space for the cast. So this is a change of the address space of the actual access, even though it is the same location, which I think is generally okay, but because if it wasn't dereferenceable, it would be undefined anyway, so that's fine. However, different address spaces may have different trapping behavior. So I think we might not allow this for volatile accesses. So we do have some questions on how to define these rules. So the main question is, are there real targets that have non-reversible or non-associative casts? Inscombine sort of assumes currently that it's okay to do a get element pointer, then an address space cast, then a get element pointer, and just reassociate those freely. But that might not necessarily be true in all address spaces. Another sort of related question is the concept of a null pointer or invalid pointer concept in all address spaces. If we're going to bother adding the data layout to data layout the null pointer value, we might as well add the ability to say there is no null pointer. So new object allocations is an area that has seen work over time that we have issues with. So the issue for AMD GPU is code that creates new values with the default address space. So for AMD GPU, address space 0 is really supposed to only be for addressing. We don't want to have any objects allocated there. We could deal with it, but it wouldn't code gen as well, and we could have to hack around it, so it'd be nicer if places just created the right address space in the first place. So the first major change we did to sort of deal with these kind of issues is we added the alloca address space to the data layout, so now you can have a stack with a non-standard address space. So previously there was no way to opt out of the generic address space assumptions because there were all these things that hard-coded the address space 0, so there was no way to opt out. So for example, in AIM GPU, 0 is a valid stack address, but under the default assumptions that is invalid. So we did have this hack where we would force allocate a 4-byte object at offset 0, so no valid object would ever appear there. We also had a problem because generic-like pointers are not fully supported in old targets, so we would have to do something creative in case a generic pointer ever existed. And when we did this, we remapped all of the address space numberings to better match LLVM's concept of the default address space, which is kind of a hack, but it does save some headaches. So last year, another field was added to the data layout to indicate the code address space for your function pointers. So that's another new field you can control. In the future, we might want to introduce a new field for constants because there are some passes today that do things like introduce like a lookup table or something like that that has the default address space that we would like to use something else. So one sort of related issue is on how global variables within address space are allocated. So everything kind of assumes an ELF-like global program behavior regardless of the address space. So this is a problem for OpenCL because OpenCL local memory is defined in a weird way. It is tied to your kernel or entry point function and isn't really a program global, although that's the closest thing we have in the AI to represent it. It's somewhere between an alloca and a global variable. We have this with a non-zero address space, and we can't really deal with the case this is used in a non-kernel function. it becomes complicated to deal with in the case that different kernels could reach a function using it through different paths. We don't have like a fixed address we can put it at that will work for all cases. So we don't really have a way to cogen this. But there are some IPO transforms that will push references to global variables into call-e functions, which are problematic. So as a hack today, we have to go through and look for this case and force always inline on them. So my question here is this even like an address space problem, or is this some kind of new IR construct necessary to represent this properly? So our address space needs are mostly met now, but there's a long tail of minor issues. There's a long tail of places that assume one pointer size. Selection DAG doesn't allow legalization for address spaces, which is a real painful point. But we're fixing this by getting rid of it. Global ISIL doesn't have these problems. There are functions that involve memory that don't use an address space parameter. However, they all need to have one. If you're doing anything in memory, you need to be aware of what the address space is. It's nonsensical to ask any question involving memory without one. I would like to eventually purge all of the default parameters of 0, but this is just a lot of work to do. There are still intrinsics that assume a default address space, including ones used for the stack, but we now do support stacks with non-default address spaces. So all of those need to add a type mangling parameter to them. And then I found that while trying to remove the defaults of 0, there are a lot of places that actually use memory-related functions in contexts that don't involve memory. So it's like a nonsensical question. So my advice is to don't use address space size 0 pointers as like your go-to integer type, which is what lots of places seem to do. For AMG, for example, that's a 64-bit pointer, and we don't 64-bit integer, and we do not want to use 64-bit integers unless we have to. 32-bit is the canonical type to use for anything. So just the pointer size 0 is not like the good integer type to use. There's a separate thing in the data layout for that, for example. Debug info is another naturally lacking area. Clang does emit debug info for the address spaces from the source language. However, we do have some issues because we change how they're accessed sometimes. We do have one pass that does change the underlying address space. So this is another example where you can't necessarily go from the IR address space back to your language address space. We do need to do something to track this cogen address space in machine IR, and we do need some additional support in Dwarf to handle this, because we need to know the language address space and how it's actually going to be physically accessed in the end for the debugger. Non-integral pointers are the other important feature to talk about. These are relatively new. They are supposed to have no assumptions about the pointer layout. So you could use some kind of fat pointer that has the high bits, has some metadata attached to them. You're not allowed to cast between integers with them, and these are kind of a work in progress and not fully defined yet. There's no cogen support, for example. The only user I know about lowers these in the IR, so we do need to do something to cogen these. I did look at adding some support to ANGP to use these for global ISIL, and we do need to do something in global ISIL that will be cast-like, because you do need to access the bits directly to legalize some things. Like, for example, if you have an unlined load you need to break down, you need to do something to hack at the bits inside the pointer. And the only defined, well, the main defined way we have now is these casts, but they're supposed to be illegal. So this is sort of my wish list for address space support, is basically to stop treating address space 0 as special, introduce new data layout fields for any assumed property. So the most important one I think is what to do for the null value, and then maybe indicate that address spaces are infinitely dereferenceable. We do have some address spaces in GPU that have implicit bounds checking and clamping behaviors, and we do have this sort of hack where we put dereferenceable U64 max T on all the arguments that have these. I would like to reallow bit cast between pointers with the same size for targets to opt out of the stricter address space cast assumptions, and better define some of the address space cast rules. But it would be nice to have some feedback from more exotic targets, because I can invent all these rules that would be nice for me, but it would be useful if we could define things in a way that works for everybody. There's occasionally mailing list posts where people ask these questions, but I never really get a clear answer on what their problem is, so that kind of information would help. So here's my review, asking to define the address space cast rules a little better. Questions?
Hi, I work on the WebAssembly target, and we're very interested in maybe using different address spaces for our upcoming opaque reference types, which would be non-integral and non-dereferenceable. Is that something that would like fit in as an address space, do you think?
Probably yes.
Okay. And can ADDRSPACECASTs be made totally illegal?
So in the sense that it's really no different than any other IO operation. I mean, you can just custom lower to an error like we do in some cases in the back end.
Awesome. Okay, cool. That's really interesting. Thank you.
Hi, great talk, and I'm really glad to see a bit more exposure of this in the community. I actually have an answer to one of your questions rather than a question of my own, which is in our target we have support for a kind of hardware-enforced fat pointer that uses a virtual address plus a load of metadata, and so we absolutely can round trip through address space 0, but the thing we don't get back is necessarily the thing we started with. So we can only do that if our insecure bit of our address space happens to overlap with our fat pointer representation, which is a dynamic property. So we would be very happy to not have the round tripping behavior. We do have out of tree patches to support int to pointer and pointer to int selection DAG operations and a pointer add selection DAG operation. And we also have lowering to 64, 128 and 256-bit fat pointer types in selection DAG. We haven't yet done the same work on global ISO. So if anyone is interested in some of this and wants to help upstream it, then please talk to me.
I thought of another question. Is it possible to have a pointer in one address space pointing to a pointer in a different address space? Is the address space a property of the pointer type?
It's a property of the pointer type. It doesn't really know anything about what it's pointing at.
Okay. So that would be possible then?
Yes.
Okay. Thank you.
Hi, John McCall. If we were able to lift all the special case assumptions about address space 0, do you think it would make sense to, sort of reserve it as some sort of like a particular address space for for example, we could use it. If we stopped making special case assumptions about 0, it feels to me like a lot of the IR would be cleaner if we could go back to assuming that the stack was always address space 0, because that's where a lot of the you talked about there being a bunch of built-ins that deal specifically in that would only need to be overloaded. That only need to be overloaded because of the possibility of using a non-zero alloca address space, and of course alloca itself, and it does create this very awkward testing problem where there's really just one specific targets that are doing this rather arcane thing. Personally, I guess I'm just maybe just declaring that I would be thrilled if we could stop making any assumptions about address space 0 and then just say, okay, look, that's the universal rule, is that address space 0 is always the stack. Would that be problematic, or are there any known targets that need to support different functions that use different address spaces for the stack?
I'm not sure. So for us, we've changed the data 3 or 4 times in the past 3 years, and
Yeah.
I'm not looking forward to the idea of doing it again. So there's sort of that problem.
Well, you're good at it now.
Well, okay. Maybe, I don't know.
Okay, thank you.
More questions? All right, let's thank the speaker again.